So continuing from the previous case, previous clip, so it is 1 minus 36, so it is minus 35 square root divided by 2. So it will be then minus 0.5 plus minus, and if you take the square root of 35, and then so it will be approximately 2.96, and then for minus I will put I. So therefore the general solution will be e power minus 0.5 t into cosine 2.96 t plus sine 2.96 t. So, and the arbitrary constants are a and b. Okay. So apply the initial conditions. 0, y of 0 was 0, so it will be, this term will be 1, this term will be 1, and then the second term will be 0 because sine is here. So a will be equal to 0, 0.16, because y 0 was 0.16. Okay, so it should be 0.16. So a will be 0.16, and then y prime of t, so we need to take a derivative, minus 0.5 t, it will be 2.96 minus 2.96 a sine 2.96 t, and yes, and then plus 2.96 b sine 2.96 t. Okay, so I'm applying the product rule, and then the second term will be minus 0.5 e power minus t, 0.5 t, and it will be a cosine 2.96 t plus b sine 2.96 t. Okay, so now we know that y prime 0 is equal to 0. So if we apply this into this here in this equation, so y prime of t is 0, this term will be 1, and in the bracket this first term will be 0, the second term will be 2.96 b. No, then I think there is some mistake. Check it again. So it is this, and then it should be cosine. Okay. So this will be cosine. Okay, so if it is 2.96 b, then cosine that term will be 1. Okay, and then minus 0.5, and then e, that term will be 1, and then a, this term will be 1, and the second term will be 0. Okay, so now we need to simplify it. So 0 is equal to, this will be then 2.96 b, 2.96 b, and then this will be minus 0.5 a, minus 0.5 a. So now we know that a is equal to 0.16. So from here 0.5 into a, that is 0.16, is equal to 2.96 b. So from here we can find the value of b is equal to 0.08 divided by 2.96. So this is approximately 0.027. So therefore now we have all the values to write the solution of the equation. So y of t will be equal to, it will start from e power minus e power minus 0.5 t. Okay, e power minus 0.5 t. A is 0.16. Yeah, a is 0.16. 0.16 cosine of 2.96 t and plus 0.027, 0.027 sine of 2.96 t. So this is the answer. So in this case, we can see that the cosine and sine terms from the previous case in the undamped situation are a little bit different. Over there it was cosine of 3t, here it is cosine of 3t and sine of 3t. Over there it was 3t, but here it is 2.96t, so it is a little bit less here. And this term shows the frequency of the oscillation. So it means that the frequency of the oscillation is slightly decreased in this damped situation, but in the underdamped situation actually. So in the end, I think the plot of this curve will be oscillating plot, and then since it is being multiplied by e power minus 0.5 t, so it will be gradually decreasing in amplitude. Okay. So this is the end of the discussion on the free vibrations, both the damped and undamped situation, but without any external force application. So the next topic will be the vibrations, also spring vibrations, but with the application of the external force. And in those situations, the equations will be the non-homogeneous equations. So here it was, the equations were the homogeneous with constant coefficients. In the next case, they will be the non-homogeneous equations with constant coefficients. And then later on, we will do one more application about the RLC circuit, so which is also a case of the non-homogeneous equations. So these are the most typical applications found in the mathematics books. Of course, there are many more applications as well, such as for the deflection of beams. So we can also set up the differential equations. So later on, maybe we can also see that application as well after doing these first two, the forced vibrations and the RLC circuits. Okay, that's all for this clip, and then for the other types there will be some other video clips.